Hello, accelerated chemistry students. This is Ms. Foley, and this is your Chapter 15, Section 2 video notes all over homogeneous aqueous systems. Let's first talk about solutions. An aqueous solution is water that contains dissolved substances. In a solution, the dissolving medium is the solvent, and the dissolved particles in the solution are the solute. Let's talk about solvents and solutes a little bit more. A solvent dissolves the solute becomes dispersed within the solvent, and solutes and solvents may be gases, liquids, or solids. Solutions are homogeneous mixtures, so the solute particles can be atoms, ions, or molecules, and if you filter a solution through filter paper, both the solute and the solvent pass through the filter. Substances that dissolve most readily in water include ionic compounds and polar covalent compounds. Non-polar covalent compounds such as methane and compounds found in oil, grease, and gasoline do not dissolve in water. However, oil and grease will dissolve in gasoline. Let's talk about the solution process. A water molecule is polar with a partial negative charge on the oxygen and a partial positive charge on the hydrogen. As individual solute ions break apart from the crystal, the negatively and positively charged ions become surrounded by solvent molecules, and the ionic crystal will then dissolve. For the process by which the positive and negative ions of an ionic solid become surrounded by solvent molecules is called solvation. So if you look at the picture on the right, you have water molecules that will surround the ionic solid. Remember, ionic solids are crystals that are made of positive and negative ions. The green negative ions are going to be surrounded by the hydrogen atoms in water, and the purple positive ions are going to be surrounded by the negative oxygen in water. Polar solvents such as water dissolve ionic compounds and polar compounds. Non-polar solvents such as gasoline dissolve non-polar compounds. This relationship can be summed up in the expression like dissolves like. Now let's talk about electrolytes and non-electrolytes. An electrolyte is a compound that conducts an electric current when it is in its aqueous solution or molten state. Ionic compounds are electrolytes because they dissociate into ions. So if we were to look at this example, we would need to know that an electric current must flow between the two electrodes that are immersed in the solution in order for the light bulb to light up. In this solution's case, we have sodium chloride ions. We have sodium ions and chloride ions flowing through water, so that's what's going to allow for the light bulb to light. Mercury 2 chloride is a weak electrolyte, so the light bulb is going to be dimmer because not all of the mercury 2 chlorides are going to dissociate in water. Glucose is a non-electrolyte because it does not dissociate in water. It stays as a whole molecular compound together. So when you look at the light bulb, it's not going to be lit at all. So a non-electrolyte is a compound that does not conduct an electric current in either an aqueous solution or molten state. Remember, it needs to be aqueous or molten because you have to have that free-flowing charge. Some polar molecular compounds are non-electrolytes in pure states but become electrolytes when they're dissolved in water. This change occurs because such compounds ionize in solution. Ammonia is one of those things. When it dissolves in water, it will conduct an electric current. And if you look at the reaction on the bottom, it will explain why. Ammonia gas will dissolve in water to make ammonium ions and hydroxide ions. Since there's ions free floating, you're going to be able to conduct electricity. It'll be weak though, because ammonia is what we will later know as a weak base. Not all electrolytes conduct electric current to the same degree. So if it is a strong electrolyte, that means all your solute is going to exist in ions. If it's a weak electrolyte, that means that only some of your solute will dissociate into its ions and some of it will stay together as the entire unit. Now let's talk about hydrates. The water contained in a crystal is called a water of hydration or water of crystallization. A compound that contains water is called a hydrate. The forces holding the water in hydrates are not very strong, so the water can be easily lost or regained. And a substance that does not have water is called anhydrous. So let's look at this example. We did this in the types of chemical reaction lab way back in chapter 11. We heated copper 2 sulfate pentahydrate and we heated off the water, and the copper 2 sulfate crystals went from being blue to being white. And then we added water back to those crystals and they went to being blue again. So we basically heated off the water and then re-added the water back. A piece of filter paper that has been dipped in an aqueous solution of cobalt 2 chloride and then dried is blue in color, which is the anhydrous. When the paper is exposed to moist air, it turns pink because cobalt 2 chloride hexahydrate is going to be pink. Now let's talk about how we can determine the percent by mass of a hydrate. We're first going to determine the mass of water in 1 mole of the hydrate. Then we're going to determine the molar mass of the entire compound. Then we're going to take the percent or the mass of the water over the mass of the entire hydrate. And there's an equation on the bottom here that will help you sort that out. So now let's talk about fluorescent hydrates. The water molecules in hydrates are held by weak forces, so hydrates often have an appreciable vapor pressure. If a hydrate has a vapor pressure higher than the pressure of water vapor in the air, the hydrate will lose its water of hydration or effloresce. We also have hygroscopic hydrates. Hydrated ionic compounds that have low vapor pressure remove water from moist air to form higher hydrates. These hydrates and other compounds that remove moisture from air are called hygroscopic. Hygroscopic hydrates have to be stored in calcium chloride because it is going to pull the water from the air, and then it will allow for the hydrate to keep its pure form. So we use a desiccant, and that is a substance that is used to absorb moisture from the air and create a dry atmosphere. So let's look at this example problem. Let's find the percent by mass of water in a hydrate. So we're going to determine the percent by mass of water in sodium carbonate decahydrate. First thing is we got to list what we know and what we don't know. Now let's go through our steps. We're going to determine the mass of 10 moles of water. So the mass of 10 moles of water is going to be 10 times the molar mass of water. So we get a mass of 180.16 grams. Remember, for every 1 mole of that compound, there are 10 moles of water. Next, what we're going to do is we're going to determine the mass of the whole compound. So we have to determine the molar mass of the whole compound, including the water. You can see at the very end, I added that 180.16. So this is 286.15 grams as the molar mass for that entire compound. Now what we're going to do is we're going to calculate the percent. So we're going to take the mass of the water over the mass of the hydrate. Notice our grams both cancel. We're with about 62.94%, which is about reasonable. Now we're going to evaluate. The mass of the water occupies more than half of the molar mass of the compound, so the percentage should be greater than 50. It is, so we're good to go. Now let's look at deliquescent compounds. Some compounds are so hygroscopic that become more wet when exposed to normal air. These compounds are deliquescent, which means that they remove sufficient water from the air to dissolve completely and form solutions. So sodium hydroxide is one of those things. If we were to leave it uncapped, it would become a solution because it will absorb the air, water moisture from the air, and become a solution. And that is the end of your video notes for section 2. And as always, all of the information from these video slides has been acquired and adapted from Pearson Chemistry's 2012 edition textbooks, resources, CD, and pearsonchem.com. Thank you so much.